Hey everyone, Professor Hank here. So today we're going to take a look at the stack data structure. We'll talk about what it is, and then we'll look at one approach that could be used for implementing the stack data structure, and then we'll finish up with some analysis. So let's go ahead and get started. So what is a stack data structure? So this is a data structure that is known as a last in, first out data structure. And it's called that because the last piece of data that you put into the data structure is going to be the first piece of data that comes out. So it's last in, first out, or LIFO. So you can think of a stack as something like a stack of dishes. So if you had a table and you were going to push a dish onto the table, then it would go onto the table. That would be your first dish. Now, if you wanted to push another dish onto your stack of dishes, you'd put it on top of the dish that was already there. And then if you wanted to add another dish, you'd put it on the top of the two that are already there. And so here what we have is a stack of 3 dishes. So the first dish we put on is at the bottom. The second dish is on top of the bottom dish, and then the last dish we put on is on the top, right? That third dish. Now, if we were to come along and try to remove an item from the stack, or plate from the stack, a dish from the stack, we take it from the top. So we would grab the top dish rather than trying to grab a dish from the bottom or the middle, right? So this is the approach we're going to take. So it is a last in, first out data structure because that third dish was the last dish I put on the stack, and it's going to be the first one that I pop off of the stack. And if I want to remove another dish from the stack, I would take what's on the top. So we're always interacting with one end of the data structure, the top. So we're always going to interact with the top of the data structure, and we're going to be able to push items onto the stack. We're going to be able to pop items off of the stack, and we're going to be able to take a peek at the stack at the top, and we'll also be able to tell if the stack is empty. So this is what we're going to include in our interface for interacting with this stack data structure. So let's take a look at these algorithms. All right, so the first algorithm that we will look at is going to be the push algorithm. And that push algorithm is going to be what we use to add an item onto the top of the stack. And so this is going to require a few things. First thing is going to be to create a node that we're going to store the data in, that we want to put in our stack. And then we're going to have to update the different links, the pointers, the references. And we're going to need to have in scope a reference, a pointer, that's going to keep track of the top node in our stack, the top item in our stack. So we're going to have in scope that top reference, and we'll also have to have whatever value or values that we were going to store in our stack in scope. So we'll need access to those two things. So an empty stack is going to have its top reference initialized to null. That's how we can tell if it's empty, and we can just check that top reference, that top pointer, that top variable, and see if it equals null. If it does, then our stack is empty. Otherwise, it's full. Now, if we want to push, then what we're going to have to do is we're going to have that top reference, and we're going to have whatever value we want to add to our stack. So the first thing we're going to do is we're going to create a new node, and we'll use a temporary reference to do that. We'll call it n, and we're going to create our new node. And then we're going to assign to the variable in our new node. So for this example, we'll just have a stack of integers and say that we have in our node definition a variable called x. So we're going to assign to that the value that we want to store. And then our node's next reference is going to need to have assigned to it the top reference. So that is what we're going to do. And so our node would have at least 2 pieces of information in it, just like any other pointer or reference-based list. And in this example, we've got an integer x, and then we've got a node reference next. So let's test and see if our algorithm holds up. And if it does, we will do some analysis to see how well it performs. Okay, so we've got our empty stack. Now we call push, and we're going to push the value 8 into our stack, or onto our stack. So the first thing that happens is right here, right? So we create a temporary local reference, and we assign to it a new node. And then we assign to its x the value we want to store. In this case, it's going to be 8. and then we assign to its next the contents of our top reference. So when we do that, we've assigned to its next null. Now there's one last thing we have to do, and that is we have to update our top reference. It needs to point to this new node here. So we're going to do t set to n. When we do that, we overwrite what's in our top reference, and that is going to be the contents of n. So now our t points to our new node, and then the algorithm's over, so our temporary reference n disappears. Right, now let's say that we want to push another value on. So let's say push 6. Let's see if it handles that. So first things first, we get a temporary reference n, create our new node, and we assign the value we want to store, in this case 6. Then we set into its next reference pointer the contents of t, contents of the top reference. Now the contents of the top reference is the memory address of the 8 node. So we're just copying what's in here into right here. So now it's pointing at that 8 node. And then we finish up by setting the contents of our top reference to n. And so now top is referring to the 6 node. And since the algorithm's done, our temporary reference or pointer n goes away. Now, the top reference should always be pointing to the top node that contains the last value that was added to the stack. Now, does it do that? It does. So what's the top of our stack? What does our stack look like, if we're to use that plate analogy? The first plate we put on was a plate that had 8 in it, and then we just pushed a plate onto the stack that has a 6 in it. So we've got that, and we've got our top reference referring to that top plate, that last thing that was placed onto the stack. Now let's say we wanted to put another value onto the stack. So we'll say 7. Let's do our algorithm one more time. So we create a temporary local reference in the case of Java, pointer in the case of C++, variable in the case of Python, and we assign to it a new node, and in that new node's integer variable goes to 7, and in its next variable we place the value we want to store in this case. And then in its next reference, we place the contents of the top reference, which is just the memory address of the 6 node. Okay, and then we update the contents of our top reference with the contents of n. So we're going to overwrite what's in top with what's in n. So that is going to change the top reference from pointing at the 6 node to the 7 node. And that means that our 7 dish is now on top of the stack, and the top is referring to the top dish, top item, as it should. So that's it. That is our push algorithm, and it works. What's at the bottom? What's at the bottom is that 8 node. It's the last node in the list. Right here, it's on the bottom. It's the first time that was put in here, so it's going to be the last one that comes out. And once our algorithm finished, let's not forget to erase our n here. Okay, so the 7 is on the top. We know it's on the top because the top reference has its memory address. And then what's underneath the 7 is the 6, right? Because the top points to the next node, which is underneath the 7, and then that 6 points to the bottom. So this is our bottom, this is our top, and this is in the middle right now, right? So there you have it. Now let's take a quick look at our performance. So how many operations do we have here? So let's take a look at this first instruction. This first instruction, we have created a new node and assigned that to a temporary variable n. So we've got 2 operations there. In this next instruction, we've assigned the value to our node. So we have an operation there. In this next line, we assign the contents of top to the next reference in our new node. And then with the very last line, we copy the contents of that temporary reference n into our top reference. So a total number of operations is 5. Now, did that change, or is there any reason for that to change based on the length of the list? No, there's no loop that happens here. There's no traversal that has to take place. So this is going to be a constant time algorithm. So this is going to be big O of 5, which no matter how big this thing is, no matter if there's 2,000 nodes or 20 trillion nodes, it's always going to be 5 operations. And so that's constant time. So we can rewrite that as big O of 1. So that is your push algorithm. Okay, now that we've got ourselves a non-empty stack, let's look at an algorithm for popping an item off the top of the stack. So we want to take a dish off of the stack and remove it so it's gone. So what are we going to do? So we're calling this thing pop, And for this approach to our stack data structure, we're not interested in retrieving the value with our pop. We're going to keep it simple. What we're going to do is we are simply going to remove the first node, and that's it. If we want to look at what's in that first node, then we're going to have another algorithm that we'll look at in a second called peek. But right now, we're just going to look at pop. So pop is going to need to have one thing in scope, and it's going to be that top reference or that top pointer, that top variable. Okay, so we're going to have to be updating it because as we remove items from the stack, right, once we move the 7 dish, then we have to update our top reference to make sure that it's pointing at the new top of our stack. Now, we can't pop from an empty stack, so we only want to update that top reference if there are actually items in our stack, if there's actually dishes on the table, right? So that's what we have to do. We have to first check to make sure that our top reference does not equal null. We only want to do something if there's actually something in the stack, right? There's nothing to do if there's no dishes on the table. So if that's true, then all we have to do is update that top reference to the next reference in the node that top is referring to. And that's literally it. It's a very, very simple algorithm. Okay, so let's try it out. So let's say that we called pop once. So what's going to happen? If top not null, so let's take a look at our top reference. Is it referring to null? No, it's pointing to the 7 node. So then what are we going to do? We're going to set t to t next. So we're going to set top reference to top next. This works just fine if we're talking about Java or Python, because since there's no references referring to that formerly top node anymore, then the garbage collector is going to come along and remove it from memory. And so our picture changes to this, right? That top reference is now referring to the top item on our stack. So the last item that was placed onto our stack, that was pushed onto our stack, which was a 7, was the first one that was removed. Last in, first out. Now, if you're doing C++ or C, there's an extra step that we have to take here, right? So this approach would work great for Java or say Python or any language that has an automatic garbage collector. But for languages that don't, say C++, well, we have to do an extra instruction in there. We still would have to have the top pointer in scope, and we would still check to make sure if our top pointer was not null. But then what we would have to do is we would have to create a temporary variable to hold on to what top was pointing at, and then we could advance our top pointer, and then we would have to issue the delete instruction. We'd have to do delete n, right? So this is only for languages like C or C++. Okay, so let's redraw that picture and see how that would change things up a little bit. And again, if this is Java, you don't have this extra step. So if it was like this, then how would this work? So if t not null, true, then we would set a temporary pointer n to t. Then we would advance our t pointer, okay? And then the delete instruction happens, removing the node from memory. Again, that example is only if we're dealing with C or C++, okay? So let's continue on. Let's do another pop. And if we do another pop in Java or Python, we check t, is it not null? True, because it has a memory address of the 6th node. So then we set t to t next, and the garbage collector would come along and free up our 6th node. Okay, we do one more pop, and we check to see if t is not null. That's true. Then we set t to t next, which is going to be null. Garbage collector comes along and gets rid of that node, and we're done. So then, if we were to do another pop, right, at this point, table's empty, so there'd be nothing to pop off of the stack, right? So when the if statement executes, if t not null, well, that's false. So this t set to t next doesn't happen. So mission accomplished. Similarly, with our C++ version, if t is pointing to null, then there's nothing to do because that if statement would evaluate to false, and then we wouldn't be deleting an invalid memory location. So let's do some analysis here. So again, a very efficient algorithm. So how many operations do we have? We have a test for this first line right there, and then we have an assignment statement, that line right there. So in the worst case, we've got a total of 2 operations. Doesn't matter how big the list is, it's always going to be constantly 2 operations. So that's big O of 2, which we can rewrite as big O of 1. So constant time. And it's 2.5 times faster than the push operation because there's fewer operations. It's fantastic. Now, if we're talking about C++, a little bit more to do here, but it's still going to be constant time. In C++, you've got an operation there, that test. You've got an assignment. You've got an assignment, and then you've got to delete. So in C++, it's big O of 4, which we can rewrite as big O of 1. Okay, so there is your pop algorithm. So next up, let's look at an algorithm for examining the top of the stack. So we're going to call this algorithm peak, and what it's going to do is it's going to need to have that top reference in scope. So we need to be able to access it. And this thing is going to check to make sure that our stack is not empty, because you can't really look at the top of a stack if there's nothing there, right? So we'll check to make sure that top reference is not null. And if it's not, then we will simply return the value in that top node. That's literally it. And this is going to be basically the same no matter what language you're taking a look at. So whether this is a C++, whether it's a Java, whether it's a Python, the algorithm is basically going to be the same. So let's see if our algorithm works. First thing we do is we check the contents of that T reference, that T pointer, that T variable, see if it's not null. Well, in this case it is. So this evaluates to false, so we don't try to return data from an invalid memory location. So we're good there. Now, what if we have a non-empty stack? So again, remember, we're only ever interacting with the top of the stack. So we don't have to worry about any other nodes that might be in the stack. We're only ever interacting with the top. So let's say that there was 8 in there. Now, if we run our peak algorithm again, we check the top reference, the top pointer, the top variable. Is it not null? True. So in this case, what do? We're going to return the contents of that node that top reference is referring to. So in this case, we're going to return 8. Now the question becomes, well, what do you return if you do have an empty stack? You have to have some kind of return statement, whether it's C++, Java, Python, whatnot. So depending on what language you're using, you have some options, but maybe the easiest thing to do is just to throw some kind of an exception. So you could just do something like throw, and then whatever exception that you decide you want to throw in this case, whether it's a custom exception or an exception that's built into the language. Okay, so let's take a look at some analysis here. How many operations do we actually have? So in the worst case, we've got a test here, and we've got a return statement here. Okay, so that is 2 operations. Alternatively, I mean, if this evaluates to true, then we're going to have 2 operations that happen, but it could also evaluate to false. And if it evaluates to false, then we're going to throw ourselves an exception, right? Which would be another operation. So it's either 2 or 2. So regardless, this is going to be a big O of 2 algorithm, which is constant time. And so we can rewrite that as big O of 1. Okay, so let's look at our last algorithm, and this algorithm is pretty much language agnostic. So we'll call this algorithm is empty, and we're just going to test the top reference to see if it's pointing at null or not, because our stack is considered empty if top is pointing to null, if it's pointing to nothing. So we'll need to have that top reference in scope. So if you're writing a class, then that reference would be a member of that class. Okay, so what we're going to do, we're just going to check if top is null. If so, we will return true. Otherwise, we're going to return false. And that's literally it. There's nothing else. There's nothing else to do here. So does our algorithm work? Well, you've got an empty list or you don't. It's binary, right? There's no other possible options. And it doesn't matter how many nodes there are in the stack. We're just checking to see if that top reference has a memory address in it or not. So in the case of an empty list, which is this guy right here, is the top reference, that top pointer, that top variable set to null? And in this case, it is. So this is true. So we return true. So mission accomplished in that scenario. And what about our non-empty list? Is the top reference set to null? No, because it's got the memory address of this first node. So we skip the first return and we kick down to the else and we return false, which is exactly what we need to do. So it works in either scenario. And again, this is going to be language agnostic. So this algorithm is going to work for C++, it's going to work for Java, it's going to work for Python, pretty much any of those languages. So we're not updating any variable. We're not trying to delete anything. We're not creating any nodes. We're not doing anything. All we're doing is checking the contents of a variable. So it makes it very, very efficient. So what are the operations? What's the count of operations that we're going to have here? So no matter what, we're going to test that top reference. So that's going to be one operation. Now, if it's true, then we're going to execute this return true statement. But if it's not, then we're going to execute this one. There's no world in which we execute both. So we definitely do this one no matter what. And then we do this return statement or this return statement. So it's one operation plus one or the other. So this is going to take two operations in the worst case. It's a constant time algorithm. So we can rewrite that as big O of 1. Okay, so there you go. There is an approach to a implementation of the stack data structure, regardless of programming language. So we took a look at what a stack is. It's a last in, first out data structure. We also talked about 4 algorithms for our particular approach: push, pop, peek, and is empty. We also looked at the performance characteristics of each of those algorithms in terms of big O. So finally, as usual, if you're a student of mine and you have any questions about the content of this video or any of the videos in our courses, feel free to stop by Zoom office hours or email me through Canvas Mail. Thanks for watching, and we'll see you next time.